Okay, so there was a question about the exercise session. It's coming a bit fast tomorrow. So after some discussion here, we decided to postpone it beyond the exam. So of course, one can return it by tomorrow or whenever. So tomorrow's session will be kind of a hint-giving session, and then you can return it. When should it be? Next week?
Friday it should be, because it will be 1 week, the Friday.
It doesn't matter if we're postponing it further. How much time do you need?
The first week of November, because the problem is that because besides course, we are also taking other courses, and we have like many homeworks, many exams this week and next semester.
Okay, it's fine by me. Yeah. What was that? What did you propose?
The first week of November.
First week of November. Yeah. Yeah, we should also give the final project. Of course, this work helps the final project because you can reuse the system model. Yeah. All right. Let's update. Maybe
one question.
Yeah, one of those days. First week of November. So that should relieve your pressure a little bit. Okay. So tomorrow will be a kind of a hint-giving session then.
Could we go through this exercise 3?
Okay,
also?
let's start. Okay, 15 minutes late, so we might actually go 15 minutes extra time. I have quite a lot of material left for the last lecture, so it might be a little bit superficial partly, but the slides should be more or less self-contained, except the last part, it's a bit more general. But the math should be self-contained. And then the material is based on these publications that are given in this slide. So you can see that I've been actually working on this area quite a lot during the last 10 years. So some of the work were done by my student Jarko, who graduated a couple of years ago, and Petri, who graduated already in 2013. All right, we're continuing with multi-cell downlink scenario, multiple antenna base stations, multiple users, each with multiple antennas. We're focusing on the coordinated beamforming scenario. So every stream is transmitted from a single base station only. This model can be extended to a scenario when a dynamic scheduling that we have let's say one stream transmitted from this base station and another stream from this base station. It extends directly, no difference. Of course, then the data stream could be split between base stations. So from architectural perspective, it will be different, but from the math perspective, nothing changes. So we assume TDD, perfect CSI in this case, but we can also assume noisy CSI, statistical CSI. That also Petri in his thesis has some details how to incorporate noisy CSI as well into this type of designs. And we focus on decentralized beamforming design. So we assume that we don't have a centralized controller that computes all the base stations, gathers all the channel states from all users between all base stations. And we assume that we have a TDD set up where the users transmit pilots, recorded pilots in uplink base stations, and then estimate the local. So locally, the channel between the base station and its own users, as well as the interfered users, right? So knowing these channels, we can also adjust the transmit beamforming rates such that the interference that this base station does not generate too much interference towards these other cell users. And likewise, this base station should not be interfered too much. Too much is, more or less this noise level should be the aggregate interference caused by the interfering bases. All right, so the aim is to do decentralized implementation, that we can do it like perfectly locally, no information exchange, but relying only on some over-the-air estimates. Or then we can have some simple scalar feedback information exchange between base stations, but no full CSI. All right. So we in this slide that we focus on the weighted sum rate maximization, but it can be generalized to other objectives as well. It doesn't necessarily, if you consider other objectives, this decentralization is maybe not so straightforward. For example, if you consider max min rate, that is much more difficult to handle in a decentralized manner because the objective doesn't decouple so easily as in the weighted sum rate. But anyways, the basic principles can be extended. Of course, one special case of this is some MSC or weighted some MSC minimization, which is actually a special case of this one, as we will see later. So where does this come from? So if you think about the rate expression per user, we can actually start from usual information. Right? So we have the system model, the received signal, basically at user K, consists of all transmissions in the cellular network. So the base station, the user I is transmitted from base station P set I. This is the transmitted signal for that given user, Xi. Xi, we assume, is generated from complex Gaussian distribution with zero mean and transmit covariance matrix Ki. Then we have the noise vector generated at the receiver. Okay. So then we can impose a question that, okay, what is the maximum rate? Let's say given transmit covariance matrices, what is the maximum rate that we can communicate between the transmitter of that is serving the user, the user K? So we can find that from the mutual information. There's the mutual information between Xk and Yk, right? And that's, of course, again, differential entropy of Yk minus differential entropy of Yk given Xk. Okay? And then we again recall that differential entropy depends on the covariance matrix of Yk and Yk given Xk. We just plug in the covariance matrices here. We have log that sum over I to K H D I to K. The base station serving user I to given user K. Okay. Then we have the transmit covariance matrix user I H D I K, and then okay, we have also this here, but I'm ignoring it because it can be removed. There has also the same same multiplier here. Oh, that. So for this one, we just remove the K user, but the summation is the same except removing the K user. So I not equal to k, HBI k, xi, HBI k, plus the integral I. Okay, so this is the rate expression. We can call this term here as RK bar. Okay, it's a matrix that we can call RK I, and that exists also here. So then we have here HBKK, KXK, HBKK plus RK bar, right? So when we take this inside this, right? So we have difference of logs is the log of ratios, and then ratio of determinants we can just take the inverse inside, and then we get this expression, right? This expression here is equivalent to this one, okay? And then the sum rate across all users is simply summing up these expressions. All is clear. So now we have a problem, optimization problem. Maximize the rate, sum rate over all users. So now we have split the user indices. So we have summing over all base stations, and for each base station, summing over all users that are served by a given base station. U sub p gives the user set, index set that is served by a given base station. And then we have per base station power constants, summing the transfer covariance matrices over all users that are served by base station. Okay, so when we look at this optimization problem, you can see that it's not, we have this log rate formula with respect to kxk is compute function. And we have the same transfer covariance matrices in the inverse. So it's actually a convex function with respect to those covariance matrices. So it's not going to be computational convex. And for this particular case, when we are focusing on the general coordinate beamforming case, we cannot use an up and down link duality to convert that to the convex form. Recall that when we have the full joint transmission scenario, that all users are served by all base stations, in that case, the whole cellular network can be considered as a one virtual MIMO array, right? That can be solved optimally with even with per basis and power constraints, because we have the solution here in the beginning. This was the optimal solution for the joint, like the ideal coherent joint transmission scenario, where every user is served by every base station, right? But in case when we have the coordinate beamforming case, this cannot be reformulated as a convex problem using the up and down link duality. So this is a NP hard, non-convex. Finding the optimal solution is basically impossible when you have large enough number of base stations and users. You can find it for very simple case like 2 users or so forth. Okay, how to solve this? There's one simple case, simple solution that you can find an approximate solution. So you can write that objective again using this expression, that we have a difference of concave functions or difference of convex functions. So you can add here now the summation over all users, right? And then subject to this power constraints. So here you can see that now we have sum of capital K concave functions and capital K convex functions. This is a concave minus concave, or concave plus convex. Right, the minus here makes this the convex function with respect to the transfer coordinates. Okay. What we can do, we can use successive convex approximation. We can linearize this part here. We can take the first order approximation, this one, then we get a concave plus linear. This is one way to do it, and then iteratively solve it. The same thing as before, that we have a concave function plus convex function, then we choose a point, we linearize it at that point, then we have concave plus linear, which is concave, and you can solve it optimally at these approximation points. Okay, then you get a new point, and then you reapproximate it at that point, resolve it, and it's guaranteed to the objective is guaranteed to improve monotony at each step. It's guaranteed because you have always a lower bound, right? So when you project it back, you always increase. Okay. So this is one way to solve it directly from the mutual information expressions, but that requires centralized processing and not so practically interesting for this particular scenario, but we can solve it in a decentralized manner. Okay. So let's solve it. Okay. First, we start with some preliminaries. MSE, mean square error reformulator. So we define an MSE matrix, which is simply the difference vectors, the mean squared error between the transmitted signal dk. Now we assume actually the signal model changes a little bit, so we include here recorders. Okay. Recorder matrix MK. This is the normalized signal vector. And then furthermore, you can define KXK to be MK permission. Okay. So this part here, you can consider this to be transfer KXI, MI permission equals KXI. Okay. So this is just plugging in. Okay, this should be double here. Plugging in the whatever at this point, plugging in here whatever received beamformer W and expressing D hat as an estimate at the output of that received beamformer. You can plug that in here and expand. You get this quadratic expression. RK, because it includes all this interference terms. Okay. This you can also write equivalent as 2 times real of this. Okay. So now when you differentiate, this is actually something that we did already in the uplink scenario. When you differentiate this MSE expression with this with respect to the W and set the gradient to 0, difference to 0, you can find the optimum W, optimum receiver that minimizes the MSE. So we get minimum mean square error receiver, right? That's a receiver that minimizes the MSE. And we have that expression given in the second, well, one of the first slides. Basically, the MMSE is simply when you solve this, WK is RK inverse HBK K MK. This is the MMSE receiver. RK is the covariance matrix of the receiving signal. YK. Okay, now when we plug in this optimum receiver WK in here, the MMSE expression simplified to this point. It's easy to see actually. You just plug in here, you get plug WK here, WK here, WK here, so you get actually 2 times this term plus but this is the 2 times, okay? Let me write it. So we have I minus MK HDK K RK inverse HDK K MK, and that's exactly the same. MK HDK. So we can call this 2 times, okay, plus M K H E K K R K inverse times R K inverse H B K K and K. Okay, so these cancel out. You can see that you have 1 minus 2 times this term plus the same term again. So we have this expression. Okay. Now, interestingly, and it's not so straightforward to see, if you now split this RK into, so RK is in fact RK bar plus HB K K MK MK emission HB K K emission, right? That's from the previous. We have the R bar K that excludes the K term. Okay, so RK equals RK bar plus the K term. Okay. So if you now plug in this expression in here, apply matrix inversion lemma, and do some crunching, some matrix operations there, you can show that these two are equal. I plus this term times the R bar BK, well, B should not be there, times this, okay. And now you can see that, okay, this is actually the same as the term inside the determinant, okay. So this term here is in fact MSE inverse. MSE, the MMSE matrix inverse. This is actually equivalent to MMSE inverse matrix. As you can see it. The term is equivalent to the term in the bottom. So if you plug this EK MMSE inverse into the Lopet formula, that's equal. So, as shown here, we can reformulate the weighted sum rate maximizes objective as log the MMSE. So first, what we do here is that we have the inverse here. So log det of inverse matrix the same as log of inverse of det. Okay, and that inverse here then goes in front. So we have maximizing the maximizing the minus log det, which is the same as minimizing. Removing the minus. It's equivalent. Maximizing the minus log det is the same as minimizing the log det. So we can express the objective as minimizing with respect to this transmit covariant, transmit recorders NK, the log det of MMSE matrix. But it's still non-convex. What we do here, the first thing, just to explain the steps, we introduce a new variable, this E tilde K. It's a PSD matrix, positive summative matrix. So we relax the MMSE expression into the constraint. So from we just take it from the objective, plug it in here. This MMSE expression. Now this MMSE expression is with respect to WK, MK, receiver and transmitter. And then we upper bound it by this new variable E tilde K, right? So obviously, when you minimize this, this inequality here becomes equality, right? So at the optimal, this is equality, and this you can plug it in. So this is the first step. So you can now see that, okay, the objective is we have a PSD matrix. This is a yeah, this is still non-convex, the concave function, right? We're minimizing the concave function. Log det is a concave function still. But the objective will be, we can handle it, so well, the details are actually explained in the following slide. So first, if you look at, again, this optimization problem, if you fix the transmit beamformer, MK, and then you optimize this with respect to the receive beamformer, WK. Just write Lagrangian here. You're back to minimizing this, because all the other terms vanish, right? And then you get the MMSE receiver. Still, the MMSE receiver is the optimal solution of this one with respect to fixed MK and fixed ET. So for fixed transmit covariance, the transmit recorder fixed E tilde K matrix, we have a closed form solution for the optimal receiver, and that's the MMSE receiver. By the way, recall that, which I didn't mention, the large scale fading A is included now in this H matrix, just to simplify the case. But if you plug in directly the original system model, we should also always carry all these large scale fading components in these expressions, just to simplify it. We assume they are included in this matrix. Okay, so now if we fix the receive beamformers to whatever value, be the MMSE. Then, first of all, the constraint here becomes convex. Because for fixed WK, this function here, the quadratic function with respect to the beamformer area. So it's a convex function. So the constraint is convex, the power constraint is convex, the linear, if you use phrase, or if you use the Copernicus norm, that's also convex. The problem is still with the log depth expression, which is concave. So what we do here is simply linearize the objective. Just like here. What we do here is that it's log depth E. It's a concave function. So we pick a certain approximation point, let's say E0K. So this happens to be, so let's say log, this one is lower bounded. Now, with the function log E0K, plus or minus, plus phrase of K minus E0 times gradient gradient is basically 0 times basic EK minus EK0, right? That's the first order approximation. First order approximation of the of this function, right? For the scalar case, if we call first order approximation, have always x0 plus the this is just a generalization of the first. Well, this is just applying the first order approximation into this log-less form. It's not so straightforward and so, but actually you can find this in the Boyd's book. I was trying to look for it. If you want to go to the Boyd's book, page 641, you will see the proof. I think I had it here somewhere. This is actually the proof. If you're interested in details where it comes from, it's well, some manipulations. Assuming that you just perturb, that you find a delta axis is very small perturbation of x, right? And then you can express some sum, and then you assume that its values are very small, so you can ignore all the other terms except the first term, right? So this is the first order approximation. And then you come up with this express log this plus trace x inverse. This x inverse happens to be the gradient of log of x times the sequence. Okay. So this is the first order express. The first order approximation of the log that function. With what we just plug in now into this expression. So what you notice that since the approximation is in the objective, the approximation is in the objective. So all these constant values. So this is a constant value here. Now we know that this gradient with respect to a ek, actually ek 0 inverse. So this is constant. This is constant. What we have left is only this linear term, like trace of this gradient times the variable ek. Now if we just denote the gradient by gki, the objective is simply this linear term. Just plugging in the ignoring all these constant terms. Of course, we can include here the constant terms here. Since they are constant, they don't affect the optimal solution. Okay, so they can be ignored. So now we have a convex problem for fixed receive beamformers. We can find the optimal transmit recoders for that given linearization point, and it can be solved optimally at that approximation point. Okay. So now we can use actually the fact that at the optimal solution, this is equality here. So what we do here is that we just place this ek expression back to the objective. Okay. And we get a nice quadratic expression for the object. The main thing here, which requires some crunching again, is that when you write the original objective, recall that we have the summation over all base stations from 1 to b, and that summation over all users that belong to set of users served by the base station. And then we have this expression PR gk I times the ek expression. Now when we plug in this ek expression in here, we have I plus we plug in that ek expression there. We have this W, well, we can write it as 2 times real WK Hermitian HBK K, and then plus W. We have trace here. Okay. RK WK RK. Now we have trace, we can trace separately. So we now function here, so we can take trace separately here. So the arcade, if you recall, that includes now all the users. So we have now actually double summation. Arcade here is the interference to given user k, interference caused by also, well, this is actually the total visit signal, including also the k user, seen as the visible k. Right? So it includes all transmitted signals from all interfering base stations, including it includes both intra and intercell interference. Yes. So when you plug in this expression in here, you have double summation. You have summation over users here and summation over users. So now you can rearrange all this term. You see that here we have VIK. We can rearrange all this. These are just it's just a summation of all this. You can rearrange the sum such that you can imagine that we have a sum over base stations here, but now you have reversed the index here. So it's VK from the serving base station of user K to any user I. Okay, and what we have done here furthermore, plugging in here the RK expression using the trace rule, the trace of AB is trace of BA. Okay, so this G, so imagine that this term, this side, so we just moved it to the other side, and the G goes to the middle. So you can see that we can decouple the objectives across base stations. We can group all these objectives, the terms in the objectives that we have a separate base station specific term in the objective, right? So you can assume that here we have a sum over all base stations, but since the only constraint, which is the power constraint, is also separate. It has per base station power constraint. So the centralized solution becomes decentralized. We can solve them in parallel. All the transmit beamformers can be solved locally at each base station. So this is the key thing. So for the fixed receivers W, the fixed approximation points, they decouple the base station optimizers instead across base stations. So we can solve them in parallel. So when we have the multiple base stations in the network, when the receivers are fixed here, the approximation points are fixed. Okay, this guy is serving this user, maybe this user, it's interfering these users. Similarly, the transmit optimizers, so this guy is optimizing the beamformers for these two guys. This base station is optimizing the beamformers for these two guys. This guy is optimizing the beamformers for this guy here. So the transmit beamformer optimization step can be done locally at each base station, just based on the locally available channel knowledge. You can see that all the channel here, we just need to know the channel from base station serving user K to the given user K, base station of the serving user, the serving base station of user K to all users in the network. So these interfered users. So this step can be carried out independently at each base station, right? Decentralized. No need to exchange information for these particles. What is more, when we write the Lagrangian, so it's very simple because we have just one constraint, right? We have one dual variable that is associated with the power constraint. We plug that into the objective, differentiate with respect to the transmit beamformers, we get a closed form solution for a given dual variable. Again, you can see that this is a kind of regularized, regularized zero forcing type solution. You have all the uses here, you have some weights here, now in the matrix form. You have the mass filter front end, right? And then you have one scalar that you need to now search via bisection. Our constraint was that Preliminaries norm of all recorders, which is the same as trace of NK resistance, should be less than. So the power constraint. So we start from one value and compute the provided transmit beamformers. We compute this power expression. We check whether that power is larger or smaller. The power constant. We keep adjusting this level until converges. The simple bisection search. Okay. So very simple to solve at each base test. You can see that this term is common for all users, so it can be just computed once. This inverse is computed once, and then we just plug in here all the users that are served by the base station B, and sum up the powers and check whether we meet the power constraint or not. So this suggests an alternating optimization algorithm where each step, it's easy to show that at each step the objective is decreasing at each step. We are minimizing or decreasing at each step. So we initialize the transmit beamformers. We initialize the transmit beamformers with some physical values. We divide the power equally. We can use match filter, for example, if you have some channel knowledge, we can use match filter as the initial beamformer, ignoring the interference. Computing this MK initial without knowing anything about the interference. Then the users estimate, assuming that we have some pilots, we will discuss about it later. They can estimate the WK, these equivalent channels, and they can compute the MMSC receivers locally, right? You see that the local solution, the WK, is simply computing the covariance matrix of the receipt signal, YK Harrison, and then multiplying that with the own channel, right? So this is the optimal MMSC, and it is obvious it can be computed independently at each user, right? Each user can compute this based on the downlink measurements. Okay. Now we have to compute this MSE weights, for which we need actually that different ways to implement this. We can exchange some information between base stations, or we can compute some extra pre-coded over-the-air signals, which we will discuss a bit more in detail later on. So this can be exchanged between base stations. So there are different implementations that some of them don't require any exchange. They rely on the over-the-air estimation, or some of them we simply exchange these matrix values between iterations. And then for fixed receiver and the approximation point, you can compute the transmit beamformers locally from this host console. So very simple steps, and usually converges to a reasonable value fairly fast, depending on the scenario. So that of course the convergence can vary quite a lot. So there are a lot of different scenarios depicted in this public cases. Okay, so every step can be calculated locally, so that leads to decentralized design. Some implementation challenges. We need to provide this WK to the receiver because, sorry, to the base station. Is when base station is computing MK, it needs to know, ideally, it would need to know WG as well as the channel estimate. So how we can overcome this need for separate estimation. Of course, if we have only the channel state available, then this W should be reported explicitly from each user to the base stations, which is impossible. So what we do is that we pre-code the pilots with this W, the receive beamformers, and the base station can then directly estimate this equivalent channel. So using W's as pre-coded pilots, we don't need to explicitly signal these W values, but we estimate directly HBKK WK. This GK needs to be shared, and there are different solutions explained, for example, in this Petri's paper. If there's time, we can discuss some of these options later. Okay. Some questions? This is the famous weighted MMSC, weighted minimum mean square error beamformer optimization algorithm for the download in the matrix form. So questions at this point? Yes.
Second step, how is MI known?
The same thing. Okay. Yes. Good point. So when the receiver, when the WK is completed from RK inverse HBKK. Okay. So there are different implementation options. Again, in the downlink, so we can assume this type of bidirectional training, where the downlink pilots are also pre-coded. The downlink pilots are pre-coded with MK, right? So what the user estimate is the equivalent channel HBKK MK. So they are not separately. We will discuss about this practical bidirectional training, hopefully this time. And similarly, in the RK, the different options, we can estimate all these terms, assume that we have orthogonal pilots available for all these terms. So the user can estimate these equivalent channels from all, just decorrelating with the non-pilots. So you can estimate all these terms for all interfering terms and then compute the covariance matrix and then add some estimated noise level there, diagonal noise, and it can compute the RK from those, or it can take sample covariance matrix. Simply sampling the received signal over antennas over a sufficiently large number of time samples and replace the E with the average over those samples. So this is a sample covariance matrix. It's not the real covariance matrix. It's a noisy version of it. But it can be okay. In practice, it's always better to construct the covariance matrix from the separately estimated terms. It's much better estimate with finite samples. Okay, so this is the matrix form implementation. Okay, just to make things complicated or simpler, there's an alternative way to achieve the same solution, but even more simplified, and doing some tricks, making the convergence fast. So recall that we can express the rate in terms of SIN per stream. Okay, we can show that these are equivalent. From the log-det term, you can actually rotate the log-det term such that it becomes a diagonal, right? So when you have a diagonal the matrix inside the log-det, the determinant becomes a product of these diagonal terms, and then the product of the log of product is sum of these diagonal terms. Right? So you can see that these are equivalent. So what happens is that when you diagonalize the log-det, these diagonal terms becomes the SIN values. So equivalently, we can write the sum rate across all bases and users as a sum over stream-specific SINs, right? So now we have capital B base station, each base station serving a set of users that belong to that serving set. Each user has a certain weight, could be 1 for the sum rate. And then every user has up to m sub k streams. And m sub k is, of course, upper bounded by minimum of the transmit and receive contacts for a given stream. And of course, in practice, also limited by the rank of the channel. The line of sight channel, there's only one stream available per user. Okay? So this is equivalent expression for the log-det form. Well, this is a special case of the log-det. We force this MSE matrix to be diagonal. Okay. And now we can. So the MK is simply MK1 to recorder vector MK. For example, if user has 2 antennas and base stations have, let's say, 10 antennas, of course, m sub k is 2, at most 2 streams per user, right? So this recorder matrix has 2 columns, one being for each 2 streams. Okay, so now we can express the SINR for given stream. So this is a stream specific SINR. Stream L of user K. Okay, this is the receiver. This would be W here. The SINR for the stream KL at the output of the recorded by m sub KL going across the channel between the serving base station of user K, and at the output of the received beamformer associated with the stream L of user K. Okay, this is the desired signal. This is the undesired part that includes both the intra and intercell interference. Right? That's the reminder. The received signal now you can write the HB K K K L D K L. This is the desired part.
Can you?
You can see. So important. Received signal at user K. We have the desired part for a given KL, and then all the interference from all users all streams such that the given KL stream is removed. Phase B I K N I J D I J plus the noise. Okay. Now we are interested in this particular simple piece of KL. So we just multiply the received signal by K with the corresponding received beamformer. And we get an estimate. Obviously, when you now compute the expectation of B hat KL minus B KL square, plug that in here and solve WKL, we get again the MMSC. Okay, so you have RK inverse that includes all the interference times KEK K N K L, and that's it. Yeah, this is the MMSC receiver vector for stream KL. Okay, and the receiver matrix WK is simply WK1 to WKNK. Okay, if you have two antennas, then two receive beamformers. Okay. All right. So this is the model. So we can express the maximization of the sum rate over in terms of SINR, where each SINR depends the corresponding transmit beamformer and receive beamformer. And then the interference is caused by all the other streams in the network. Okay. And again, by looking at this expression, it's clear that it's again non-convex problem, not jointly convex with respect to Q, W, and M. And then you have terms both at the numerator and denominator.
That should be W in previous. U should be W.
Yes. Okay, let me fix that immediately. That's it. Okay, fixed. There was another mistake somewhere there. Okay, I'll fix that. So, but otherwise, this will stay there forever. All right. Okay, that's fixed. Right, so now we have this optimization problem. Okay, all right, so we had actually the MMSC receiver given here. Again, if you plug in this SINI expression there, write the Lagrangian difference with respect to WK, it's guaranteed that that you have the closed form solution, which is actually not directly the MMSC receiver. It's a the MMS the rate maximizing receiver, which is actually scaled version of the MMSC. But we can safely replace that receiver, there will be a scaling here. But we can replace that with the MMSC receiver because from the MMSC, from the SINR perspective, the scaling does not matter. Right? If you plug in here whatever scaling, it affects all terms equally, right? So the scaling disappears. If you add here scaling 1000, that same scaling is here, it cancels out. So we can replace that with MMSC receiver. The mean square error expression, when we plug in the that term in here, you get the MMSC expression. Okay, you minimize this, you get that. When you plug in the optimum MMSC in here, there's some processing, you get this corresponding. So SINR plus 1 equals MSC inverse. MSC inverse is equal to SINR plus 1, or SINR equals MSC inverse minus 1. So just like in the matrix form, we can replace, in principle, we can replace this with epsilon inverse. Okay? But now in the scalar form. So we can have exactly the same steps like here. This is the matrix form. This is in the scalar form. We could have here, okay, this is a bit complicated here, but we could just plug in here epsilon tilde inverse, and this would be epsilon tilde, right? So we have now a convex constraint. We introduce a new variable epsilon tilde, and we have an inverse of epsilon tilde that in minus goes in front, so we're maximizing the minimum, maximizing the negative, which is minimizing that term. So we have a log of epsilon, this is a concave function of epsilon. We could linearize that, and we would have a optimization problem. Exactly the same steps as in the matrix form. So we do here an extra step to even further speed up the process, the convergence. So we actually introduce here a general function g of TKL. This is kind of a upper bound. So we add here a new variable TKL. It's multiplied that function g that acts as an upper bound for the MSE expression, which is here. And then we impose a constraint that is g take TK is monotonic and log concave, meaning that plugging that in the g function there, the objective is concave. Right? Plugging that function inside the log concave means that when you plug that function inside, the objective is concave. If you plug in here an exponential function, that becomes a linear, right? Because log and exponential they cancel each other. And this is actually something that people do later. So now using this constraint, now the objective is a concave function, but now in the constraint we have both sides are convex. Okay, so we have a difference of convex. Difference of convex means successive convex approximation. So we replace, so we again use the same old first order approximation, right? So we have this convex equals convex, which we cannot handle in the convex smaller than convex, which is the same as convex minus convex. So non-convex problem. Difference of convex, it's a sum of convex plus concave. So what we do here is that we again linearize this function here. Or we have this one. We linearize the right-hand side. What you can see here is that this is now again a upper bound of this convex function. When we solve this, convex. Sorry about that. This is a convex function. This is a convex function. Okay. When we solve this, you can see that the original function is always feasible. Original function is always strict equality before the final convergence, right? So when you project it back, you always increase the objective, right? You can be, because it's loose, so you can always improve to make it tight. Okay. So now, after approximating that right-hand side, this is a convex function with a linear function, and using G that satisfies these properties, we have a concave objective, convex constraints for all streams, and then power constraint, which is convex by default. Them all. Okay. So that also leads to iterative algorithm, just like in the previous case, alternating optimization, starting with a feasible transmit beamformer, feasible that it satisfies the power constraints, then computing for fixed beamformers using pilots, recorded pilots from all the base stations. Users can estimate the equivalent channels, compute MMSC receivers locally, and then again locally solve the transmit beamformers. We will see actually how the transmit beamformer looks like later on, and then update these values and proceed. What's that?
This procedure always converts.
Yes, it has monotonic convergence. We will see. Every step has a unique solution, right? And every SEA update improves the objective, makes the constraint loose. Constraint is loose, so you can always make it more tight. It improves the objective. MMSC is always optimal, right? So it improves the SINR.
I mean, the global solution, there are two loops, right?
There are two loops, yes.
The outer loop is the alternating of contamination.
Yes.
The inner loop is the
Yeah, that's a good observation. That to currently actually in this case you don't because the SEA has a closed form solution. You can show that for this particular case, in general, you should have for fixed receiver, you should have an SEA that you should basically update the SEA until convergence before updating the MMSC receivers, right? That would make it a bit slow. But we can be shown that in this particular case, you can see that this approximation point update has a closed form solution. It's you can do this. You can include all the updates in one loop, and you can still show that it has monotonic convergence. Let's see how it looks like. Okay. Let's first consider a special class, important class of these boundary functions, G. alpha is 2, the log 2 of 2 is 1, so it disappears. That's one. Then actually we have just this non-scale. We just summing up this t k here. And actually in the special case, when alpha is 2, this becomes 1. And let's see. What's 2? This. Wait, how did it go? 2. Thing is that this is when you use alpha 2 here, then you basically the end user actually have a t here. I don't remember now what happens there. This goes here. Alpha is 2, this should simplify. It's the same as, you know, approximating the objective directly. Okay, but the weight should have here. Okay, weight is not here. Okay, I don't remember now the details. So you can show that it's equivalent to directly approximating the objective instead of approximating the constraint. Okay. All right. So this is the linear approximation of this that function. This is the function value at point I, and this is the difference of the function. And you have that it's a linear. You can see that the linear function around the point of approximation. I, which is from the previous iteration. So it's a convex optimization problem. It's a linear objective, convex constraints for all streams, and then for each base test. Again, you can see that this problem decouples across base tests. The constraints are decoupled by the base test specific power constraint. The objective is coupled, but we can write this as a sum and separate. These terms are base test specific, and also these terms do not depend on. These MSE terms are also decoupled across base tests. So we can also solve this for fixed receivers. We can solve this locally at each base test, just like the matrix version. So now when we plug in, when we write a Lagrangian for this, we get again a closed form solution for transmit beamformer. And not surprisingly, it looks exactly the same as for any other objectives that we have covered, like min power beamformer in the single cell case, looks exactly the same. Max min SINR, MSE, all these have the same structure. Again, we have the regularized, weighted regularized MMSE type transmit beamformer. But now, of course, these lambdas, they reflect. The lambdas are the dual variables that are associated with the MSE constraints. Mu is the power constraint, the dual variable for the power constraint. And these lambdas reflect this weighted summary maximizes an object. So now you can actually solve, from the KKT conditions, we have this direct correspondence You can find the lambda k expression. It's a one-to-one correspondence between TKL from the previous. And then you can find also the TKL from the complementary slackness constraint. So from the complementary slackness constraint, meaning that its lambda values have to be positive. So these constraints are always met with equality, meaning that lambdas are positive. So you just assume now at the optimal solution that here's an equality, and you can solve TKL from this expression directly. And that's given. So you can see that in this expression of tk I plus 1 term depends on the previous term, multiplied with some constant with it as an alpha times this term. So you can actually see that this, you can think that it's kind of a step size. How much you want to change this earlier. So how much you want to change this or how much updates you want to add to the previous approximation point. If you make this small, meaning that you use large alpha, the update is small, you use smaller alpha, something between 1 and 2. You have a larger update. So this is now, you can, if you make this term small, means that you are using something value between alpha value between 1 and 2, because you cannot go beyond less than 1 with this function. You can speed up the conversions. That's somewhat heuristic, but what we noticed that if you treat this log alpha as a step size, you can now changing this exponential function of the approximation to the base, you can speed up the convergence of this algorithm. The problem is that if you choose this alpha to be too large, it does not converge, starts to oscillate. So you can make a kind of heuristic update of this step size that we have a iteration specific weight here, that in the end, if I recall correctly, this will drive this solution towards alpha 2.
Alpha.
Log E, actually, it writes.
No, that term disappears. At the beginning, it is log E, then it goes to log alpha.
Well, that's for sure, yes, for beta larger than 1. Okay. But anyways, you can play with this alpha and beta to oh yeah, right. So in the beginning, you subtract something from this alpha value. Okay, so you make the update smaller, and then that term vanishes, and then I increase it, and then you have the exact update there, which converges monotonically. You can see that we did some tests in multi-cell environments, set a number of users, receiver transmit receive antennas. The baseline scenario is the weighted matrix form weighted scenario that we introduced earlier. Right. And then another method which is has exactly the same convergence behavior. You can actually sort of AI or they were published the same year. Parallel works. So you can see that by properly adjusting these step size parameters, in the beginning, let's say that you have three iterations, you fix your iteration budget. Let's say that you are allowed to exchange these pilots 3 times. Right? So you're not interested in the final convergence. You just want to iterate 3 times. So you should have as quickly converging algorithmic behavior as possible. You can show that you get fairly large gains by properly tuning this heuristic step size. So this is the SCA method that is explained in more detail in this PhD paper. So basically, what I explained in the preceding slides. On the other hand, when the number of iterations increases, obviously all the solutions they start to converge to the same local optimal solution. They converge to the same solution if you start with the same, on average at least. Initialization, yes. I cannot say that they converge to even with the same initialization, that they converge to exactly the same point for a given standard realization, but at least on average they perform the same. Might be that they converge to the same point if you initialize them the same way. But you can see that, okay, after some iterations, no difference whatever step size you use. But in practice, when you have less time to iterate, this is very important. Okay. So now, how to do this in practice? We have actually quite recent communication magazine paper, if you're interested in details how this could be applied to 5G radio using the existing 5G 3GPP new radio standard and related signaling and pilot resources. It's explained in this communication magazine. I would just give a brief overview. How this alternating optimization approach can be implemented in practice. First of all, we assume this coordinated beamforming set up that we have only local CSI. We want to have a decentralized optimization that all these access points locally compute their transmit beamforms. One can, of course, it is one possible implementation. If you have a cloud CRAN, cloud radio access network, where everything is centralized, then you might very well do centralized processing and joint transmission and so forth. Right? So then, of course, you don't need to worry about the local CSI because you would gather all the information to centralize it. But here we assume that we have local processing, and this base station has only knowledge about these locally measurable channels. Right? This base station has this channel knowledge, but not the blue links, right? Only the local CSI. So, how we can plug in the this alternating optimization algorithms into practice? So we can use so-called backward forward or forward backward training. Like we can basically in NR the frame lengths can be very short. We can go, the numerology goes down to 0.125 milliseconds per frame, and each frame you can you have 14 origin symbols. Right? If you have a frame has 14 origin symbols, then we can assume that okay, this that we can use this so-called mini-slot structure that is available in 3GPP NR, where we can basically send two origin symbols, either in uplink or downlink. So we construct a certain mini-slot structure that we can fit within one frame, one slot, actually, so it's a slot for the NR. Slot consistent of 14 origin symbols, where we can actually quickly switch with some guard time, switch between, let's say, uplink, downlink, uplink, downlink, right? So if this is, for example, 0.125 milliseconds, we could switch, let's say, three times or 3-4 times within one origin symbol. So we could maybe have 2 iterations, like uplink, downlink, beamformer updates during one slot. We can have another slot. We can continue, then we can have 2 times more iterations. Right? And then we can switch to data transmission. We can have downlink only transmission, for example, uplink only transmission. And we can keep updating still. We can have some symbols associated with reference symbols, where we can further have, let's say, downlink here, or uplink here, downlink here. And these are the data symbols for which we use actually this optimized beamformers. So we can construct a frame that consists of, for example, 8 slots. That would be 1 millisecond. Right? And some parts of the maybe first or second, the first one or 2 slots could be associated with this bidirectional framing, where we actually transmit pre-coded pilots both ways, so we can estimate these equivalent channels that HBK, NBK, or WK, where is an HBKK, right? In TDD. Yes, this is assuming TDD, right? So we do it very quickly switching between uplink and downlink, transmitting, receiving, transmitting, receiving, transmitting, receiving.
No, use the reciprocal cable. Only just needed to evaluate the downlink or uplink channel.
If you're optimizing downlink, the receiver estimates all these. So we need to assume that now we have a synchronized network, like all these base stations are transmitting at the same time. So if this is downlink transmission, all the receivers now estimate these equivalent channels from all the base stations, construct the MMSC beamformers. MMSC receivers here use these MMSC receivers as transmit beamformers. The base stations then estimate, all the base stations estimate all these equivalent channels from all uplink user transmissions, and they can construct these equivalent channels. Okay, so we have backward pilots, forward pilots. We can do it for both uplink and downlink. If we are focusing on downlink optimization, backward is uplink, forward is downlink. And then we are processing the beamformers for both things, and then possibly also exchanging some information. But this is something that we do not want, because exchanging something over backhaul, it slows down. So we want to actually come up with some strategies where we can use these backward forward pilots only to recover everything. So there are different strategies how to do this. in practice, we can use extra signaling in uplink or downlink to be able to recover some different terms in those beamformer expressions. I'm skipping those details, but they are all relying on this alternating transmissions by base stations and users. Right? So this is one way to show this. You recall these expressions. We have the transmit beamformer expression and receive beamformer expression. So in the transmit beamformer expressions, we have these equivalent channels, the green ones, and then we have these dual variables. And in MMSC receiver, we have just this equivalent precoded channel. So the user only needs to estimate this equivalent channel, right? You can think this as one vector, matrix times vector. It's one vector. If these pilots are precoded with these terms, what is estimated at the user is just one vector, corresponding to that case of L3. And then you estimate for all, if you know the pool of pilots, for all the pilots that the user is aware, it estimates it. Of course, in practice, this is never perfect, and there's always a finite number of pilots available, right? So you have to do some proper pilot allocation. You should avoid so-called pilot contamination. Right? You're reusing the same pilot, but if you assign the same pilot, let's say, far away enough, the contamination from that reused pilot can be reduced. Right? But that's always there. In practical systems, nothing is ever perfect. Here we assume, for simplicity, that we have this orthogonal, perfectly orthogonal pilots available. But obviously, if you think about cellular network, it's by default no limits, millions of users. So there's no way that you can assign orthogonal pilots for every user, but you have to reuse them. So it's a trade-off between channel estimation quality and the overhead. Right? The more pilots, the more overhead, less resources for the actual data. So you have to find the sweet spot. All right, so these two terms are easy because they can be pre-coded. They can be pre-coded by the pilots can be pre-coded by those beamformers, and the equivalent channels can be estimated. Right? Receivers estimate these effective downlink channels. Base stations is a downlink optimization. Base station estimate these effective uplink channels. Okay. Now the problem is how to deal with these dual variables. These are important weighting factors. One solution is to incorporate this lambda into the precoder. So precoders are weighted by these lambdas. If you weight the precoder by lambda square root, right? If the user is able to update this lambda, it just includes it in the and actually it is able to estimate the lambda because so user can estimate MSE, local MSE, and that depends on the local MSE. So this recorder can be weighted by square root of lambda, and the base station is able to reconstruct this term. Okay. The problem is that this would be now weighted by square root lambda. Okay. And that's not exactly what we want. So what we can do is that the base user actually then sets two sets of pilots. One weighted with square root lambda, another one with lambda. Okay? And then using those two sets of pilots, we can reconstruct without any feedback between base stations. This is another one possible implementation. Of course, there's some extra overhead of this extra pilots. Okay? So this is a trade-off. Or we can have these lambdas exchanged over the backbone or any hybrid between. And there are some more involved cases explained in these references, but okay, it's a bit difficult to explain. So I'm skipping those. But it's basically the story is around the fact that we need to be able to reconstruct those transcript beamformers with lambda knowledge, right? So there are different ways how to reconstruct from different types of measurements, and there are some examples of different strategies. Strategy A I don't exactly remember what are the fine details between these strategies, but there, one is to rely on the backhaul and just doing the MMSC receiver update. I think it was the strategy A, and then doing something more advanced, exchanging some extra or doing some proper, a bit different type of pre-coding, not just using the MMSC receiver, but doing something more intelligent. We can further speed up the convergence in the beginning, which is very important. We want to have fast converging solutions. We have this limited number of backward forward iterations available. Right? The important thing is to have as fast initial convergence as possible. And actually, Petri also compared this matrix weighted, what we introduced earlier, and the scalar weighted. They are overlapping. The basic scenario that we use the MMSC receivers as the uplink recorders. Okay, there are a lot of details how this speed up can be implemented in practice, but doing proper pilot recoding can give significant increase of performance. Like after 3 iterations using just the basic alternating optimizers and gives you the 8 bits per second. Doing something clever in the beginning gives you already 13 bits per second. So 50% increase. Okay. Just a couple of points about use of pilots and the direct estimation of this beamform. This is just a highly simplified scenario about the let's say the full-blown cellular setup. Okay, so as we have been discussing, we can carry out this estimation using a global knowledge of these pilot sequences. Right? So the base stations there can be some signaling the initial access, or they can be hard coded whatsoever. These are the pilot sequences that are used. Okay, these are the pilot sequences that are assigned to you. These are the other pilot sequences that you should be estimated for the interface. And that leads to optimally or ideally global pilot resource allocation. So we can actually use this. So there are two approaches to compute the beamformers. As I mentioned, we can estimate all these screen-specific channels based on these known pilots, or we can also estimate these beamformers directly. And that actually can be beneficial, especially when we have overlapping pilot resources. So let's see how this happens. So let's assume a very simple setup first. Okay, let's see that the base station here, let's consider just one base station. It's transmitting some signal x1. This can be a precoded signal with so it's sending two signals in parallel, each weighted with possibly orthogonal sequence. Right? It's V1 and V2 are orthogonal. Okay, there can be another sequence which is not orthogonal, so neither V1 and V2. Okay, that's ignored in this equation. So let's consider just two sequences. So basically, base station could be serving two users, right? Each associated with user one is channel. User one signal is associated with the sequence V1. This is actually a row sequence, and the length of the row vector is the length of the sequence. Okay. The longer the sequence, the better channel estimate and vice versa. So this is actually a matrix. So this is a number of antennas times the number of symbols in the sequence. So this is the sample matrix. So this is the receiver basically samples at the antenna outputs, analog to digital converter. It takes samples for all. Or can take some oversampling as well, of course, of the transmitted pilot sequence. Right. So this is a sample matrix. Ideally, ends up R number of receive antenna times the length of the sequence. So knowing V1 and V2, the user can then reconstruct the receiver. Receive beam format, MMSC receiver. So in this particular case, when we have just two transmit streams, we're just serving two users. So the MMSC receiver, okay, this is the W again. Ideally is okay, it's X1. X1 contains actually the beam format, the precoders and the data. It's not. It should have an actually expert data inside. But anyways, so this would be the MMSC receiver of the user one ideally. So we can first construct the equivalent channel H1 X1 by decorrelating with the known sequence V1 from the received signal Y1, right? Because the other term, because we assume V2, V1 to be orthogonal, this disappears, right? So we get the desired channel, but we get some noise. Okay. Of course, the noise contribution, the longer the sequence, the smaller the noise contribution. Especially when we normalize the noise by the length of the sequence. So now we can just sum up these two, and we get the desired part, right? But then we get all these noise terms. If this B1 and B2 are not orthogonal, we get also all the cross terms. This would be the contamination, pilot contamination. So if you take an expectation, you get certain noise variance for all this noise. Okay. So that's possible, right? What you can do also is to simply see the MMSC receiver as like a least square, minimizing the least square between the known sequence V1 and the optimal beamformer W1 permission times the visit sample matrix. When we solve this with respect to W, you get actually Y1 permission inverse times Y1 B1. When we plug in those terms in here, you can see that again, the same terms here that are required for the MMSC, but then we have all this noise there. If B1 and B2 are orthogonal, this disappear. If B1 and B2 are long enough, these terms disappear as well. And this becomes N0 on. So then we have a optimal MMSC. And then the match filter, we can match filter front end, actually. This one here. For the orthogonal case, again, this term disappears, but then we have all this noise. Okay. You can actually show that this method is direct by beamformer estimation. You don't have to necessarily estimate these individual terms separately. You should not do that actually ever. And then reconstruct the inverse from those individually estimated terms. This is always much better. And what is more, it can also handle the cross terms. When you have B1 and B2 non-orthogonal, you have some matrix structure here that is already included in the inverse. So this, when you invert, we are inverting this with some contamination terms. This inverting always suppresses also the contamination between particles. When you do this separately, if you have some contamination here, actually you are just including this contamination directly into this vector estimate. And so you lose this matrix information that is available in this direct estimate. So this contamination is in the matrix form here. The direct estimation is projected into this interference contamination vector. So you lose some information there. You lose some suppressing capability. It's a bit complicated to explain and you have to understand, but if you're interested in more details, you can read the communication magazine. It's easy to read, no math, and it points to other papers where it's studied in more detail. Okay. Well, I need to go through all the material. This concludes the course from the lecture perspective. Any question at this point? Or can we also practical questions? If not, tomorrow is the hint session. We will during this week we will prepare the final project definition. And as I mentioned, it will be about this decentralization of the mean power beamformer design. You have already some templates from the previous exercises and also from the latest exercise, which you can reuse for this final project. It should not be too much work, I hope. All the details are included in this final slide set.
We go through to
Remember
this.
to also give some feedback via web audio. I'm not sure, but web audio actually might be closed. Now we are Peppi.
Can
We will figure out the details.
you hear me?
Tomorrow.
Okay. All right. Thank you, and good luck for the exam and the rest of the exercises and final project. Thank you.